Have you ever wondered why we don't float away into the sky? This question might seem simple, but it's the gateway to a profound understanding of the universe. It's the question that led to the discovery of a fundamental force of nature: gravity. When you think about gravity, you might picture an apple falling from a tree, or perhaps you remember that it's the reason we don't fall off the earth. But what if I told you that these are just the surface-level explanations? What if I told you that gravity is more than just a force that pulls us down? So why don't we just float away into space? It's not because the Earth is sucking us down like a giant vacuum cleaner. No, it's something far more fascinating. It's because of an invisible, yet incredibly powerful force that pervades the entire universe. A force that we are going to explore in depth in this video. Gravity is the invisible force that keeps us grounded. Gravity, in simplest terms, is an attraction. Picture this. You're at the top of a hill with a ball in your hands. You give it a slight push and off it goes, rolling down the hill. But why does it do that? Why doesn't it just stay where it is or roll upwards? The answer to that is gravity. Gravity is like an invisible hand that's constantly pulling everything towards the center of the Earth. It's the force that keeps us grounded, literally. Without gravity, we would just float away into space. Now, let's think about that ball again. As it rolls down the hill, it's not just going downwards, it's also moving closer to the center of the Earth. That's because gravity pulls everything towards the Earth's core. So whether you drop a feather or a bowling ball, gravity draws them both towards the center of the Earth. You might be wondering why the feather seems to fall slower than the bowling ball. That's due to another force called air resistance, but that's a story for another time. In essence, gravity is an invisible force that governs our lives in more ways than we usually realize. It's what keeps the planets in their orbits around the sun. It's what causes the tides in our oceans, and it's what makes apples fall from trees. And yes, gravity is the reason why that ball rolled down the hill. It's the reason why when you jump, you always come back down. It's the reason why we don't float away when we let go of something. Gravity is all around us, working silently, invisibly, keeping us anchored to our planet. It's a fundamental part of our universe, and understanding it helps us understand the world we live in. So, gravity is the reason why things fall to the ground when we drop them. Gravity is not just a theory, it's a law. A law that was put into words by one of the greatest minds in history, Sir Isaac Newton. This 17th century English physicist and mathematician is best known for his law of universal gravitation. But what does this law really mean? It's a concept that describes gravity as a force that exists between any two masses, any two bodies, any two particles. It's a force of attraction that pulls objects towards each other. Imagine you're holding two apples. According to Newton's law, there's a gravitational pull between these two apples. It's incredibly tiny, so tiny that you wouldn't feel it. But it's there. The same force is at work between you and the Earth. It's why when you jump, you come back down and don't just float away into space. Newton's law of gravitation states that every particle of matter in the universe attracts every other particle with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. In simple terms, the bigger the objects and the closer they are to each other, the stronger the gravitational pull. Now you might think, if that's the case, why doesn't everything crash into each other? Well, that's where the inverse square part of the law comes into play. It means that as the distance between objects increases, the force of gravity decreases rapidly. This law is universal. It applies everywhere in the universe. And it's predictable. It allows us to calculate the gravitational force between any two objects if we know their masses and the distance between them. It's this predictability that has allowed us to send spacecraft to other planets and even beyond the boundaries of our solar system. It's how we can predict the orbits of planets around the Sun and the Moon around the Earth. Gravity, as described by Newton, is an invisible force that governs the motion of our universe. From the falling of an apple to the movement of planets and galaxies, it's all explained by this one simple yet profound law. Newton's law of gravity explains why planets orbit the Sun and why the Moon orbits the Earth. Gravity isn't just an Earth thing. It's a universal phenomenon, a cosmic dance that happens everywhere in space. Now let's take our understanding of gravity and venture beyond our home planet. You've probably seen footage of astronauts floating around in space, looking weightless and free. But here's a little twist to that story. Astronauts aren't really weightless. They're constantly falling. Yes, you heard that right. Astronauts, the International Space Station, and everything on it are falling towards Earth. But they're also moving forward fast enough to keep missing it. This creates a state of perpetual free fall, giving the illusion of weightlessness. This is the same principle that applies when you feel weightless at the top of a roller coaster ride. But gravity's influence extends much further than just causing things to fall. It's the invisible artist that paints the grand portrait of the cosmos. It's the sculptor that shapes galaxies, and the choreographer that arranges the celestial ballet of planets around their stars. Every celestial body, from the smallest asteroid to the largest galaxy, exerts a gravitational pull. This pull is what keeps planets like Earth in orbit around the Sun. Without gravity, our planet would simply float away into the cold, dark void of space. And it's not just about keeping things in place. Gravity plays a crucial role in the formation of celestial bodies. When particles in a nebula, a giant cloud of gas and dust, start to pull together under their own gravity, they can eventually form stars and planets. In a larger scale, gravity is the force that brings galaxies together to form clusters, and clusters to form superclusters, creating the large-scale structure of the universe. So when we talk about gravity, we're not just talking about why things fall down. We're talking about the fundamental force that shapes the universe, drives its expansion, and orchestrates the cosmic dance of celestial bodies. Gravity is the glue that holds the universe together. It's the unseen hand that guides the cosmic ballet, the silent force that shapes the cosmos. Without gravity, there would be no stars, no planets, no galaxies, and certainly no life as we know it. Gravity affects more than just physical objects. The pervasive nature of gravity extends to even the most intangible aspects of our universe like time and light. Now let's take a deeper dive into these fascinating effects. Firstly, let's talk about gravity and time. Here we enter the realm of Einstein's theory of relativity. According to this theory, gravity can actually slow down time. Yes, you heard it right. This effect is known as time dilation, where time passes slower in stronger gravitational fields. So if you were to spend a significant amount of time near a massive object like a black hole, you would age slower compared to someone far away from it. It's an interesting thought, isn't it? Next, we move to the effect of gravity on light. Now, light doesn't have mass, but gravity can still influence it. This phenomenon is known as gravitational lensing. It's the idea that gravity can bend the path of light, much like a lens bending light to focus it. So when light from a distant star passes by a massive object, the light's path curves, causing the star to appear distorted or in a different position than it actually is. This effect has been observed multiple times in astronomy and serves as a powerful tool for studying distant galaxies. Lastly, let's touch upon gravitational waves. These are ripples in the fabric of space-time caused by some of the most violent and energetic processes in the universe, like the collision of black holes. Albert Einstein predicted the existence of gravitational waves in 1916, and a century later, in 2016, their existence was confirmed by the LIGO and Virgo observatories. So as we can see, gravity's influence extends far beyond just pulling apples down from trees. It shapes time, bends light, and causes ripples in the very fabric of our universe. Gravity is not just a force, it's a fundamental part of the universe. Gravity is an incredible force that is everywhere. We've taken quite a journey today, haven't we? We've simplified this complex concept into something more digestible, explaining how gravity is not just a force that keeps us grounded on Earth, but a universal law that governs the movements of celestial bodies. We've explored the law of gravity, delving into the intricacies of this unseen force that pulls objects towards each other. We've also ventured beyond our home planet, highlighting the omnipresence of gravity. It's not just here on Earth, it's on Mars, it's on Jupiter. It's even in the vast, seemingly empty expanses of space. We've also dived into the effects of gravity, not just on us, but on the universe as a whole. It shapes galaxies, it bends light, and it even dictates the flow of time itself. Gravity, the invisible force, is what keeps the universe in harmony. Remember, it's not just keeping your feet on the ground, but it's also keeping the stars in the sky.